Let's talk about reactions that we can do with aromatic compounds. And the first one we want to discuss briefly is oxidation at the benzylic position. So anytime we have a substituent on a ring, we look at the carbon directly attached to the aromatic ring. That is called the benzylic position. So on this molecule that I have here, there are two benzylic positions. On this molecule down here, this is a benzylic carbon, and this is a benzylic carbon. So oxidation at the benzylic position involves changes at that carbon. And if we use sodium dichromate, sulfuric acid, and water, this mixture here, we get a product that is a carboxylic acid. And so you'll notice that both of these alkyl chains turned into carboxylic acids, and this chain even lost a carbon. And so it doesn't matter how many carbons you have on your alkyl chain, as long as you have at least one hydrogen in the benzylic position. This sodium dichromate reagent will cleave a bunch of carbons off, if there are a bunch. In this case, there was just one, and it will create carboxylic acids at the benzylic position. So now we have a means of installing carboxylic acids at the benzylic position, provided we start with a alkyl chain. And in this case, I got two because I had two benzylic positions. You can certainly start with one alkyl chain and get one carboxylic acid. Let's look at the product of this bottom reaction. And you'll notice there are two hydrogens here at the benzylic position, and I hope that you understand there are 0 hydrogens up here at this T-butyl group. So I do have two benzylic positions, however, only one of them has hydrogens. So I'm going to maintain the tertiary butyl group, and I'm going to create a carboxylic acid at that lower, longer chain. And again, you'll notice that I lost 1, 2, 3, 4 carbons. I cleaved this bond right here, and I installed a carboxylic acid right at that benzylic carbon. So as long as there's at least one hydrogen, we can turn that alkyl chain, doesn't matter how long it is, we can turn it into a carboxylic acid. The next reaction that we want to discuss is free radical bromination. And that's going to stem from the chapter on free radicals. If you were in my class in first semester, you probably didn't cover it, but you can review portions of that chapter if you need to look at the reactions here. And so we're going to use NBS, and you'll see that I have NBS written here as an acronym. I've defined the molecule here. It stands for N-bromosuccinimide. Here's the bromone, here's the N, and this 5-carbon ring, or 5-membered ring with 2 carbonyl groups, is called succinimide. So we have N-bromosuccinimide. It's essentially a source of bromine radical. Bromine radical, of course, is that guy. And so the product in this case is going to take any benzylic position that has a hydrogen again, and I'm going to add 1 bromine. If you're careful with this reaction, you can add just 1 bromine. If you're not careful and you let it go forever, or you add a lot of NBS, you could potentially add a bunch of bromine. So we need to be a little bit careful here. But you see that the important thing here is that I took this unfunctionalized aromatic ring. This is called toluene, incidentally. I took toluene and I turned it into benzyl bromide. And I have a functional group now at the benzylic position. This is a good leaving group. I can undergo substitution type reactions with this and add some more carbons or add other functional groups to this molecule. I can make it much bigger. I can use it in synthesis. So this really gives us a very good tool of taking this relatively unfunctionalized molecule, adding a functional group, and then we can proceed with other synthetic steps. So how does this work? Well, it is a radical mechanism, which means we're dealing with 1 electron at a time, and so we're going to draw some single-headed arrows here. NBS, in the presence of light, will dissociate into this 2 radical species. And if I draw the H back here on toluene, what I'm going to do with this bromine is I'm going to remove the H, forming HBr, and leave half of the bond behind, forming a radical. So those are my 2 single-headed arrows trying to show that we formed a radical, or I'm sorry, we used a single electron from each of the bromine and the hydrogen, and then the other electron in the bond is going to create a radical at the the benzylic position there. So now I get that radical is what I formed with my 3 green single-headed arrows, or fishhook arrows. What I want you to do is prove to me that this is resonance stabilized. So go ahead and pause the video, figure out how many additional resonance structures you can draw using these single fishhook arrows, single barbed arrows. Okay, you should be able to have put a radical on each of these 3 positions in the ring there. So you should have 3 additional resonance structures showing that that radical is resonance stabilized. It is called an allylic radical. And that's why it works in this position. So we also form HBr. Right, that is what this and this arrow are showing. I'm forming the HBr. If we mix HBr and NBS, so we're going to use some more NBS. Again, this is the NBS. We're going to create bromine molecule, Br2. And that can react with my radical. I'm going to use my same double-headed arrow push. And you can see that this results in the product plus an equivalent of Br radical. And so this Br radical can then go ahead and react with more of the starting material to create more of the benzylic radical, or the allylic radical. And so this is the basically 2-step sequence needed to take the non-functionalized benzylic position and turn it into an allylic bromide. So let's look at an example down here. Here we have 2 benzylic positions. And if we're very careful, we can probably put a bromine on this position because it comes from the more stable radical intermediate. So here we form the product, and that's because this intermediate here is more stable than this intermediate. Because this is a tertiary radical and this is a primary radical. So we can selectively brominate, if we're careful, the tertiary position over this primary position. And one last thing I want to point out to you, this reaction tends to work best when there's no other functional groups present. And so we prefer to use an unfunctionalized aromatic ring like I showed here or here, and that's just because NBS, HBr, and bromine radical tend to react with other functional groups in ways that we don't really want them to react. So it's best to start with an unfunctionalized aromatic ring and install a bromine using the NBS mechanism.